Thank you that you left this an open problem for me. Basically, fixing that issue was my diploma thesis. And this was the starting point. And I think the funniest time I had with Jurek was in Penn State when we shared for some time, when I was a postdoc there, the same office. And well, I learned very much from Jurek, in particular Polish invectives. When he wanted to express his happiness about any emails, there were some words, and I had no idea what they mean, and I asked him, and then he explained, and then I knew, okay, better not to know them. But he had no punching ball there, but I was impressed how strong these keyboards were at that time, that at least according to the sound, I was always afraid it will not last longer than 1 month or so. But I think everything worked fine, and I very much enjoyed it that we could share the office. In my talk, I want to speak not about what Hanno said, this and what you mentioned, because this is not that what Jurek did, but more what I did. So I want to speak on several uniqueness issues that are, at the first point, really related to Jurek because he was involved, or that became later some example or some scheme that has been used to prove further examples. Maybe I come, if time permits, and usually time does not permit, I come to these issues later. But let me start with, I just forgot that I have this practical device. Let me start with some overview. Why it could be interesting to study the issue of uniqueness in quantum gravity. Usually one starts with some sort of canonical quantization, and what are we given? We are given some classical system, and say with first-class constraints. Then you have many options in the game. First, you have to choose some separating space of phase space functions. Then for the quantization, you have to choose somehow some representation, maybe not in the mathematical sense, on some kinetical Hilbert space. Then again choose some sort of group averaging. And then, okay, you get to the physical Hilbert space. Again, this is in one of these famous papers here. And as I've learned quite recently, a colleague of us have abbreviated this not ALMM or ALM squared T, but a bit differently, namely mafia. And I was a bit confused about this and thought maybe there's some reason for that. And if you believe in mirror symmetry and take the reverse order of the authors and consider more the relevant letters in the names, then you really get mafia. So I think this was probably the reason why this was named in this way. So what I want to focus on is today basically the first and the second issue. Therefore, I remove all that. And even more, I want now first to discuss the issue of how to choose the elementary variables. Okay, let us be given Ashtekar gravity. I can, I think, be very brief here, just for completeness, to fix the notations. We have some basic functions. We start with these parallel transports here, these smeared Derivation fields. And then we consider cylindrical functions on the connections. Means that we first take a finite number of parallel transport functions and concatenate them with some smooth function. Of course, one can take some continuous function, but for today, I want to consider smooth functions here because if we want to consider derivations here, then we need some derivatives, and then it's better to have smooth ones. The advantage of the whole business is that diffeomorphisms, for instance, can be easily implemented. I mean, we have here some geometrical structures like graphs, surfaces, and smearing functions. Then there's a natural action of the diffeomorphisms. Yeah? So, and having done this, we get immediately to the celebrated lost theorem. They are not in the reverse order. Zoll does not sound that nice, therefore lost is given that theorem. It relies on the so-called holonomy flux algebra that is given by all words in these cylindrical functions and these derivatives, space just called x, and these two relations plus linearity. So we have the compatibility with the Poisson bracket and that the multiplication of cylindrical functions is compatible. So then one can show that there is some invariant state with these properties. And the funny thing is, indeed, under certain assumptions, namely that dimension is at least 2 of the manifold, that the hypersurfaces, diffeomorphisms, and the geometrical issues are semi-analytic, in some sense that they're basically analytic, however, may have some sort of kinks or whatever. And these smearing functions should have compact support. Then this omega 0 is, and now the first time we have unique here, then it is the unique state on H that is invariant with respect to bundle automorphisms. Basically here diffeomorphism is sufficient in that. So, and as I am a mathematician, okay, what to do now? Yeah, one shall prove it. And for that, I, of course, use the blackboard. Because when I checked the lost theorem, I think I found a shortcut that allows me to prove it here, not with quite a long reference to several other statements. But let's see. Maybe you find that I'm wrong, but then also helps me a bit to see. Okay, what can we do first? Let's say we have some omega, some state that is invariant with respect to the bundle automorphisms. In the first step, we do not need this. We only have to show that if omega is positive, which is normally the case, we assume that we have a state, then omega is continuous on cylindrical functions. And yeah, the proof is not really difficult. We may assume, let me do this here. First, we may assume that we are given some real function in CIL. Otherwise, take real part plus imaginary part, and you get maybe a different constant for the continuity. Okay, if this is real, as it is a bounded function, we know it has a norm, a supreme norm, and if we assume that R, for some sense, is larger than the supreme norm, then we know that R plus minus psi is positive, always. Strictly positive. Therefore, we can take the square root. It doesn't matter for the cylindrical function, it just means that we take the square root of the smooth functions on g to the n, no problem. Of course, it's real. We can multiply and put a star for convenience. But what we can do now is that we can take omega of this expression. This is now positive. I mean, this idea has been in the paper. I mean, that's not new. But what is this? This is nothing but r plus minus psi. In other words, we have here r omega 1 plus minus omega of psi. This means that the modulus of omega psi is smaller or equal to omega of 1 times the norm of psi. So this means it is continuous. So fine for this. So what we need in the second step is, now we need a very important thing. Now we need the symmetry of the system. The symmetry, here the diffeomorphism symmetry, immediately implies that we get that for the derivations, and maybe I shall, oops, is it already necessary to? I'm too slow. Actually, one should put some heads on these objects because we have to factorize by these relations. But as I'm doing the uniqueness theorem, and as this would just implement additional conditions, it doesn't matter. I mean, uniqueness does not mean that there is exactly one. It just means there is at most one. And that's what I'm going to prove. Then we get immediately that this is the case, and this is in the algebra. And yeah, then we have, for abstract nonsense, Gelfand-Naimark theory, that then we already have this for any element of the holonomy flux algebra. Okay. How to prove this? Okay. For some reason, let's say here A. Okay, this is this great trick of the origin lost paper. We introduce the bilinear form using the smearing. We just say, okay, we take the respective smearing function, write some fixed element of the Lie algebra, and I take this expression. Okay, bilinear and all that. Next, I may consider some coordinate system because it's local. Therefore, it's important to have semi-analyticity. Otherwise, it wouldn't be the case. And I fix there some vector E. This is parallel in my surface, and this should be S, and the smearing function given there is F. Okay, it should have compact support in S. What I can do now is, what I wanted to take, okay, I define some function. This is a function here in the Rn minus 1, and I may tensor it with a function h along this line with the property, this is 1 at 0. Then we get, if we define the following function, for sufficiently small lambda, we may now define this function and putting here some x into, we here just get some function, and then we can see that this finally is a diffeomorphism. Diffeomorphism for small lambda. Yeah, and then finally we define the function f of x is this. What we now see is this is a diffeomorphism. Therefore, this is nothing but f itself, it's coming from here, plus, well, lambda chi. The funny thing is that our chi is on our surface equal to f. Therefore, if we now evaluate this using the invariance of omega under diffeomorphisms, we get plus 2 lambda real part. So this cancels out, and this is true for all lambda. But then this must be 0. And that's what we wanted to prove. The only issue is that we have to, again, just, the only thing we have to also use is that any of these derivatives can be written as a linear combination of such localized derivations, because we have partition of unity. This is the only part. So now we are almost done. Using the CCR relation, we now get that omega, if we, and now there's not this multiplication, this is really derivation of that object, that this is 0 for all and this can be proven quite easily. I prove it this way. Not this way, this side. We know that this is up to an I or a minus I. Oh, it doesn't matter. Should be 0 anyway. This way start minus x times a. Oopsala. Now we know this is 0, just as, I mean, for abstract nonsense. And then we get here, we can turn it around, getting here x star. Sorry, a is psi, which is nothing but this. And of course, we have to turn it around. But the problem is, as we assumed at the beginning, that these derivations having real valued labeling are symmetric. We have this. We could also start with x star, x star. But then we get this is again 0, therefore this is 0. Okay, and now, and this is the point where in the original Lost paper, the Lost people referred to a quite technical paper by Jurek and Anja Okov. But with the denseness result, it's again a one-line proof. Or maybe at this blackboard a two-line proof, or let's see. First, I take a spin network function. And I can now apply some Casimir operator for a particular edge. But what is the Casimir operator? If you take the Lie group, it's just the, I mean, maybe with some prefactors depending on the group, but SU2 is no problem. Take just the sum of the xi's squared. But then we can write it this way. Upstairs. Yeah. This is nothing but the Laplace E on psi. However, this is nothing but lambda, and now the Casimir invariant of the representation that labels the edge, and we now get this. However, this means that any spin network function up to the constant one can be written as x of some other function. But we know omega of these functions vanishes. Therefore, omega of psi vanishes for all spin network functions up to the single one. Done. So we know one, and these objects span dense subspace. And we are done by number one, the continuity. Proven. Yeah? Pardon me? We have the derivatives for the. This is the definition of the. This is, I think, even in this proof on the area operator, for instance, how the derivatives look like or derivations look like, and it's just given by the derivative with respect to. It just works. It just acts on the psi gamma part, living on g to the n, and as we even have a product, as we have a spin network state, as we have just a product of matrix functions on certain edges, we can restrict ourselves to a certain edge. And on that certain edge, it is just a left invariant vector field. And this gives, if I take such expression, the corresponding Casimir. And this is known then to have this eigenvalue. If you find an error, please let me know, yeah? But I was a bit annoyed because it was too simple in some sense, yeah? But I couldn't find a mistake. I do not want to say, unfortunately, I did not find a mistake. I'm happy that I did not find so far. But therefore, I thought maybe I can present it and the sort of birthday present to Jurek make things a bit simpler. In particular, as from my point of view, I consider a theorem more important and more trustworthy the more one can shorten the proof over time. That's a quite reliable criterion in mathematics. Therefore, I'm more happy now with the loss theorem than with my theorem, because I was not able really to shorten that proof so far. Technically, it can be done a bit easier, but so far, I think it's the shortest version I know so far. Okay. So I don't see this. Good. So we have done this. Now the question is how to do this, possibly for, okay, yeah, thank you, I forgot. How to do this for cosmology. And well, first we have to check what we have to do for cosmology. Probably you remember that page. There's one difference now. It's chapter 4. But what I want to do is just make some changes to make cosmology out of it. Okay, what do we want? We want to implement homogeneity and isotropy. Then we, of course, have to restrict our basic functions to these homogeneous isotropic connections. And then we no longer have the smearing here. If we go to the standard P or CP variables. And of course, the cylindrical functions also have to be restricted to R, which is isomorphic to the affine line in the space of all connections that just characterizes the homogeneous isotropic connections. And I refer to R3 at the moment. They form a dense subspace in this set here, in the continuous functions on R that vanish at infinity, and the almost periodic functions. Okay, the derivations are quite simple. They act, this T is what also is given by C. That's quite simple. And then the diffeomorphisms get to residual dilations, and then, yeah, the action is also quite simple for the derivations. We get just some lambda. With some comment you will probably make later, because Jonathan realized that he does not like this version with lambda. He prefers some other. But we'll come to this. So now we can go to the cosmological holonomic flux algebra. I just call it this way. That's again the old one with lost. And now I also said, okay, mirror symmetry is good, and it looks better. It's now the theorem because it's by Jonathan, Hanush, my former PhD student, and Thomas. But it's EHT doesn't sound good. Therefore, I said the theorem. What my name is here, there was some 0 equals 1 in the proof. I removed that. Therefore, I put it here. Okay, maybe I can go back and you see only slight changes. We have here the star algebra, again of all words. Now, yeah, which functions do we want to take? The derivations can refer to derivatives. Okay, what to do? We should have closeness with respect to derivatives. And then we have here a dense subalgebra of A, and this is then the basis of the holonomic flux algebra. And now we have to prove that this is unique. But this is really no problem, because we know how to prove it, and most of the proof is already at the blackboard. Therefore, this is the lost part. Now, let's do the part. Or maybe I can start here. Okay, first, omega positive means omega is continuous on SIL. Let's do it more general on B. No changes. The only problem, y is the square root of r plus minus psi, again, is in B, indeed. And for that, one has to think a little bit. If this is an element of B, and if f is some analytic function with convergence radius r, what do we get? Well, then we, of course, get that f times psi is equal to the sum here. And exactly, this is now not necessarily in B, but in A maybe, because It could be in the closure of B, which is A.
Can you remind us what the B was before?
There, assume, or there. It's given there. This is the C0 plus C almost periodic. And B is just, are those functions whose derivatives stay in A. Because, I mean, if you have a function vanishing at infinity, the derivative need not vanish at infinity. But take one of these e to the minus t squared. Okay. Oh, when is it start? I thought about half. Okay, okay. So then I have this, but I have the chain rule. And this just means that I have this. And this is an A again. And by induction, I get the proof. Therefore, it is indeed in B. Let me do it this way. Therefore, F is in B again. And therefore, as this function, square root of r plus minus z, is an analytic function, I can reuse that. So we have the first part. The second part, symmetry. No, that's easy. That's really easy. Ah, no. Okay. What to do? Omega of x times x. I can ignore the stars because it's self-adjoint, or symmetric, not mathematically self-adjoint. And of course, this is now equivalent with respect to, I don't have it here, to the action of the dilations. But they just give a lambda squared. Immediately implying that it's 0. And as you want to have here a 2, but you can have a 42 or 73 or whatever. Just take some whatever. Alpha. We have 2 alpha. Unless alpha is non-zero, it's always 0. Okay. Check. This is the same as we have done here. And now the denseness result is, and again, you said, oh, we have to do this with the measure, and it's the same, like here. The idea, the trick is completely the same. Just consider that the span of 1, and then we take the derivatives of e to minus lambda t and the derivatives of e to minus t minus t0 squared. They give the AP part, and they gives the C0 part, and they span again dense subspace in A. And now we are done with this. So, perfect. Okay. Because it's discussion probably. Yeah, I see. Okay. Then maybe I discuss a little bit, but now there are several other uniqueness results. What I've not speaking about is, for instance, the Ashtekar-Lewandowski measure, which is quite famous. I haven't used it here. I mean, we never got to A bar or something like this. There are other several uniqueness results, so that I want to go to the end to conclude. Jurek has indeed proven much more than I've presented here. Has found, proved, created, inspired, generated, and whatever, many uniqueness results. However, it is sure not the last one I want to consider today. I have a final statement. It doesn't work, doesn't matter, or it's too far. My nice theorem. Maybe I have to do this and then this. Yes. Yeah, final uniqueness theorem. Okay, yeah, sure. Jurek is unique. Yeah? And as I'm a mathematician, I have to prove it. And, you know, as a mathematician, I know how to make short proofs. It's obvious. And that's what I wanted to prove.
Okay, thank you very much. So, question, comments?
There's at most one. I mean, not Jurek. We know that there are many Jureks here, but it's similar. Like it may be a joke that is only familiar to Germans. Es gibt nur einen Rudi Völler, was a famous singing in the football stadium some years ago. But yeah.
Okay. So, any more comments or questions? Okay, if not, let's thank Christian again.